This is an example of a survey spectrum that would be difficult to use to quantify these samples based on a survey spectrum alone. And the reason this is a problem is because we have peaks such as these peaks here, which represent not just one photo emission line, but a sequence of photo emission lines from the different elements that we have in this sample. If we look here, you might see that copper correlates nicely with these two peaks. However, when you select aluminium, you can also see that aluminium correlates with these peaks. And what's more, we have chromium in this sample, as you can see by this peak here, so we should also have a chromium 3s that also sits beneath this particular structure. So in order to quantify based on photo emission lines, we must perform some kind of peak fit on at least the simpler of these peaks. So the aluminium 2s, copper 3s will be the peak that we'll look at in terms of a peak model. The aluminium peaks are really the only pair of peaks that we have available to us for quantifying by aluminium. So although copper includes the copper 2p, we really must work out the intensity of the aluminium based on these high energy peaks. So what we'll do is consider the aluminium 2s and the type of peak model that we might apply to these data. Now, because this is a profile and we have an evolution of these aluminium peaks, we can see how the aluminium oxide varies, and we can see also how the aluminium metallic form and the copper varies. So it gives us a chance of working out the peak model that we should use for these data. The first problem with a peak model is working out what the line shape should look like. So it's very useful to have data such as these that are from the Latrobe database that include a copper 3s as part of the data set, and we can see from these data that the line shape appears as a consequence of the copper 3s is very Lorentzian. And we can get an idea of what this might look like if we introduce a line shape that is very Lorentzian, an LA 1,243. Let's try fitting these to the data, and then reducing the amount of Gaussian broadening. So now let's make that 70, say, and say fit. And looking at these data in terms of the type of shape that we should expect, it may not be identical to what we see in the data set that we're really interested in, but at least it does show that we're looking for a full width half maximum that is somewhere between 2 and 2.5, and that a Lorentzian shape would be expected. Similarly, we can look at other data that involves aluminium, and if we focus on an aluminium peak, we can see that a Lorentzian-like shape fits this aluminium 2s quite nicely. This is aluminium phosphate, and it's once again data that's in the Latrobe database. So it's very useful to have these type of data when you're trying to work out the types of shapes that you might expect in a peak model, such as the depth profile that we're interested in. So when we consider the peak model, we can happily introduce two peaks that should be somewhat Lorentzian, and then we have another peak that has a slight asymmetry. This is typical of aluminium metal to have a slight asymmetry. So when we display these, let's put up an annotation table containing the peak model. You can see we have Lorentzian peak for the copper 3s, and we have a Lorentzian peak for the aluminium 2s, and then we have a slightly asymmetric peak for the aluminium metal. And taken as a whole, we need to have a peak model that applies equally to all of these different conditions for the surface throughout this depth profile. So we're applying the same shape and allowing the peaks to move a little bit, because when a surface is being hit by ion beam, as in the case of this profile, you might expect some differences in the surface and the relationship between oxides and metals to occur. So we're introducing asymmetry in the metal, Lorentzian in the oxide and the copper, and generally we are trying to maintain the same peak model throughout the entire profile. Finally, to assess this profile that we've organized in terms of these 3 peaks, we could use the custom report, select components. So I've copied through from these selected VAMAS blocks the components that are defined on these VAMAS blocks. These are only the metal oxide for aluminium and the copper, and if I press apply, I then get a table of results, and if I say create profile, I end up with a profile showing how these peaks are behaving with respect to one another throughout the depth profile. And at least in the first instance, the shapes that we see here certainly look plausible in terms of what we might expect from this depth profile. So this lends some support to the peak model that has been defined on the aluminium 2s and copper 3s intensities.